When we studied the weak field limit of general relativity, which is also known as the post-Minkowskian approximation to general relativity because you expand the field around Minkowski, we found that in vacuum the gravitational field in a certain gauge, etc., satisfies the wave equation, which means that there will be gravitational waves. These are the gravitational waves that we are going to study now. First, we are going to study the propagation. So we are going to write the Einstein equations again in vacuum, far from the sources that produce these waves, and we are going to study how these waves propagate outside of matter. Well, let me start by reminding you what was this weak field limit. Okay, we found that expanding the metric around Minkowski as a perturbation that was controlled by this parameter chi, okay, such that chi squared was 16 pi g, and now I am going to use all the time units of c equal 1. Well, we found that the Einstein tensor, okay, started at first order in chi, and that it had this expression. So to the derivatives of h, which I will define later, but it is the trace of h mu nu, plus 2 times the symmetrized derivative of the divergence of h, plus d squared h mu nu, minus eta mu nu, d squared h, minus d rho d sigma h rho sigma, okay, plus terms of second order in chi, which is the same as of second order in h. So here h is just h mu mu or h mu nu eta mu nu, because this field h mu nu is going to be treated as a special relativistic field. So the metric effectively is just eta mu nu, okay, in this approximation. D squared here is the Lambertian. So this is just d mu, which is d0 squared minus di. Okay, which I may also write as d0 squared minus, plus di. And here in general, I will distinguish between upper and lower indices. Okay. On the other hand, the expansion of the energy momentum tensor gives you at first order what we call the Rosenfeld energy momentum tensor, which is a special relativistic energy momentum tensor that you get from the gravitational one by replacing the full metric g mu nu by eta mu nu, plus terms of order chi or h. Okay, now if you plug this expansion into the Einstein equations, okay, you arrive at the lowest order to an equation that we wrote in this form. So this is an operator d mu nu of h equal to t mu nu Rosenfeld, and this operator is just everything that you find here at first order. This is d mu nu of h. And these are the linearized Einstein equations, lowest order. Okay, we said that this operator d mu nu and then these equations are invariant under transformations, gauge transformations of h mu nu of this form. Epsilon nu, okay, where this epsilon mu is a vector, a set of functions of x. Okay, this is something that you can check with a bit of patience it is not very hard to do it, but I am not going to do it. It's really straightforward, and the result has to be that it is invariant. Okay, so I will ask you to believe this or check it if you want. Then we introduced a variable that we called h bar mu nu, which was equal to h mu nu minus a half of eta mu nu times the trace h. Okay, let me, if we want to rewrite this equation in terms of the variable h, this linearized Einstein equation, in terms of the variable h bar, we have to, to write h as a function of h bar first. So if we take the trace, that we also call just h bar with no indices, this would be h minus a half of 4, this is 2, and then h, so h bar is just minus h, or h is minus h bar. So you take this result here and you find that this is h mu nu minus a half eta mu nu now plus h bar, and the result is that h mu nu is, well, it has the same expression if you interchange bars and no bars. Okay, so now you can come here to this operator d mu nu of h that we have introduced here and replace h by h bar. I'm not going to do the calculation explicitly. This is done in the lecture notes, and what you find is that these equations become, well, take this form in terms of h bar. So some terms just disappear. Sorry, this is not d squared, this is the rho, h bar rho, and nu plus eta mu nu, the rho, the sigma h bar rho sigma, and this is equal to kappa t mu nu Rosenfeld. Okay, and then we imposed a gauge condition. Okay, we said that you could always impose this gauge. This was the Donder gauge, and then you see that with this gauge, this equation, well, this term just vanishes, this term vanishes, and then in this gauge you just get h bar mu nu equal to chi t mu nu Rosenfeld. And in vacuum, so outside of the sources, you just find the wave equation for h bar. Okay, this is what we want to study. The first thing that we want to check, okay, because in fact we are going to study this point in detail, is that you can always write h bar satisfying this condition, okay, this gauge. Or in other words, that given any initial h bar mu nu, you can always perform a gauge transformation, okay, such that the transformed field satisfies, well, let me put it like this, such that partial mu h bar mu nu prime is 0, because this is the condition that we want to impose. In order to prove this statement, well, we write explicitly the transformation. Okay, since we have defined this gauge transformation in terms of the variable with no bar, I rewrite h bar in terms of h. So this is just eta mu nu and h prime, and then as we said, this is just partial mu epsilon nu plus partial nu epsilon mu minus a half eta mu nu and then there is a factor of 2 and partial alpha epsilon alpha for the trace. You have this is h prime is just the trace of this, plus the original variables, okay, because it's h prime mu nu is h mu nu plus this, and this combined gives you the original h bar mu nu. Okay. Now we impose the condition that we want to be satisfied, that the divergence of h bar prime is 0. Okay, and this is knowing that this is this, so we have this plus partial square epsilon nu plus the mu epsilon mu minus these factors of 2 cancel, and this is the nu, and let me write it this way, epsilon instead of alpha I use mu now. Okay, now I see that these two terms cancel, and okay, this condition, the solution for this condition is that d squared epsilon nu has to be minus the divergence of the original field h bar mu nu. Okay, this is D'Alembert. This equation can always be solved, okay, because there are solutions for the Green function, and you just have to plug whatever divergence of h bar you have, and you always find a d squared epsilon nu that satisfies this condition, and that brings you to the Donder gauge. So we just proved this. We have used 4 gauge transformations. There are 4 different components, okay, in 4 dimensions, and we have used this to restrict to impose 4 restrictions on h bar, okay, each of them. So these are 4 restrictions, 1 for each value of this index nu. So out of the 10 original components of h bar, we have been able to fix 4 of them. Okay, you can think that you have removed them as degrees of freedom. Okay, you have found relations between all the components of h bar. As a matter of fact, you have eliminated 4 out of the 10 degrees of freedom, so you still have 6. However, and this is why the counting of degrees of freedom, when you know what are the gauge transformations are, is not so straightforward. You can still perform additional gauge transformations that preserve the Donder gauge. In other words, the Donder gauge condition does not fix completely the gauge. If you now perform transformations, gauge transformations, that satisfy this condition, okay, so then, well, they don't modify this the Donder gauge, but you can use them to remove additional components or additional degrees of freedom of h bar. It's more precise because you don't remove components in general. What you do is you find relations between them, so there are less of them which are independent. Okay, there are another 4 possible functions of this kind that you can use, and this means that you can remove another 4 degrees of freedom. So here you have 10 minus 4, and here you get 6 minus 4, and these are the 2 degrees of freedom. The number of degrees of freedom that you have is 2, which coincides with the 2 polarization states of a spin-2 particle. And this is basically what you expect for the propagation in vacuum of the gravitational field. Well, something that I didn't mention, but it's kind of obvious. Okay, this is the wave equation, and in the wave equation, the velocity of the waves appears explicitly. Here, in units of c equal 1, you don't see anything, but you know that the velocity of the gravitational field or the gravitational waves is 1 in units of c equal 1. So gravitational waves propagate at the speed of light. Well, a bit later, we are going to use explicitly this kind of transformations to reduce to simplify as much as possible the form of the gravitational waves, of the gravitational wave field, h bar mu. Okay. Now, if we are outside of the matter sources, because we can do this, because we assume that matter sources have matter has a compact support, T mu has a compact support, and you can be far away from them. Okay, we can quantify this in terms of the characteristic wavelength of the gravitational waves. So, in these terms, we talked about the near zone. This is where we made this post-Newtonian approximation. Now we are outside of that zone, okay, and we cannot ignore these gravitational waves anymore, and we are far away from matter, okay. Well, then in that case, we have that the gravitational field satisfies this equation. If you take the trace, you see that since theta mu nu is constant, you see that h bar also satisfies this condition, and in just because of the relations that we found between bar and unbarred fields, this means that h mu nu, the original field, also satisfies the wave equation, okay, in this gauge. So we are going to study gravitational waves using the original variable h mu nu. The solutions to this equation are well known, and you know that they are superpositions of the simplest solutions, which are of the form of a wave. Okay, and in general, these solutions have this form. First of all, there is a tensor, which is constant and may depend on k, which is something that I'm going to introduce now. And this tensor is called the polarization tensor. Well, this is very similar to what happens in electromagnetism, but in electromagnetism, the polarization tensor is just a vector. And then the typical sinusoidal function, sorry, not plus, but times sine of, this is the vector k that appears here, okay, times x alpha. What is k? You know this very well, but I have to repeat it for completeness. Okay, the first component, the zero component, is just omega, the angular velocity divided by the speed of the wave, which in this case is the speed of light. Remember that omega is just 2 pi divided by the period, so this whole thing is just 2 pi divided by the period times c. And this is the same as 2 pi, the frequency, because the frequency is the inverse of the period, divided by c. And these are the spatial components, and these spatial components can be written as 2 pi divided by the wavelength times ni, which is a unit vector that just points into the direction of propagation of the wave. Okay. The first thing that you have to do is check that this indeed is a solution of the wave equation. Okay. It's a linear equation, so the most general solution will be a combination of solutions of this kind, of simple solutions of this kind. We plug this into the wave equation, and well, this is constant, so you have two derivatives of the sign, and this is x alpha, so you get k alpha the first time, and then k alpha the second time. These two k's are contracted because this is the D'Alembert, the indices are contracted. So you find that d squared h mu nu is minus epsilon mu nu of k. Then you have k alpha, and then sine, okay, of k beta x beta, or if you want, minus k squared h mu nu, better. Okay, so the condition for this to be a solution is that k squared is a null vector. With this decomposition, k squared is just 2 pi squared, and you have nu squared divided by c squared minus 1 over lambda squared. This equal to 0 is the same as nu times lambda equal to c, which is the condition that you have for gravitation, for waves that propagate at the speed of light. Okay, so this is satisfied. Okay, just put it. Okay, just a simple check. Okay, still we haven't imposed the Donder gauge in this solution. We just said that this is a solution, but h mu nu has been assumed to satisfy this the Donder gauge condition. So we compute now, instead of just the a derivative with free index, we take the divergence of h mu nu, and we find that this is epsilon mu nu. You get a k mu from the derivative and a cosine of k dot x. You also need a partial nu of h. H is just the trace. Okay, let me just write epsilon, and this gives you k nu cosine k dot x. So partial mu of h bar mu nu is just, well, you have an overall factor of cosine kx, and then epsilon mu nu minus a half of epsilon, which is the trace, times k nu cosine of kx, and this has to be 0. The implication is that the polarization tensor has to satisfy this condition. So this is due to our choice of gauge. Okay, this constrains the possible polarizations. As we said, imposing the Donder gauge only eliminates 4 degrees of freedom. In this case, it means 4 constraints on the possible polarizations. The polarization tensor has 10 components, is symmetric, just as h mu nu is symmetric. So we still have 6 independent components of the polarization tensor. But also, as we said, this the Donder gauge doesn't fix completely the gauge. We are still free to perform another 4 independent gauge transformations with parameters satisfying the wave equation, in fact. Okay, and we are going to show that you can use this remaining or residual gauge freedom to set some components to 0, which are these are conventionally chosen. Okay, probably you can choose something else, but this has been shown to be convenient. Okay, very convenient. And the choice is that all these components are going to be 0 for I equal 1, 2, and 3, and also that the trace epsilon, which explicitly is epsilon rho rho, is 0. These are 3 conditions and 1 more condition. So these are the 4 remaining conditions, and this leaves us with only 2 independent components in the polarization tensor. So before we study which ones are the independent and the independent components and what the rest look like, let's prove that using these remaining 4 gauge transformations that do not take us out of the Donder gauge, you can impose these conditions on the polarization tensor. Okay, so this condition is evidently tied to h prime 0 I. Okay, this is what you want is that after performing a gauge transformation, epsilon 0 I will satisfy will be 0. Okay, epsilon prime. But you know that this is okay, the original field epsilon 0 I with this sign plus partial 0 epsilon I, okay, minus partial, sorry, plus partial I epsilon 0. Now, well, there are too many epsilons here. Those with two indices are clearly polarization tensors, and these are the parameters of the gauge transformation. Okay, now, because these epsilons have to satisfy the wave equation, we can choose them of this form. Not so surprisingly. Okay, now they have, well, if I write the mu, this would be alpha mu cosine kx. Well, this k is the same k that appears here, but it could be something else, as long as k squared is 0, so k is a null vector. And alpha mu doesn't have any particular meaning. The fact that we choose the same k here and here is because, well, we are going to see that in order to cancel this sign, etc., it's clear that we need to choose the same k, otherwise we cannot find a combination between this and this. And what we want to do is not just to solve this wave equation, we want to find solutions of this wave equation such that we can set epsilon prime 0 equal to 0, or this whole thing. Okay, so this is why we choose this in this way. So having made this choice, okay, we have that this is still epsilon 0 I sine kx. Then we have the derivative of epsilon I with respect to x0, and this gives us, okay, gives us a minus, gives us alpha I because it is epsilon I, and then gives us k0. And because this is symmetric, this will give us alpha 0 ki. Okay, and this times sine kx. This is what we find after the taking the derivative of the cosine, and this minus sign that I have already taken into account. So what you find is epsilon 0 I minus alpha I k0 minus alpha 0 ki sine kx. It is clear that this is epsilon prime 0 I, and we are going to set this equal to 0, which is a condition on this alpha I and alpha 0. So this condition can be now written as a linear equation for alpha I and alpha 0. In fact, this is a set of three equations. We can write them in this way: alpha 0 ki plus ki alpha 0 equal to epsilon 0 I, which is the thing we start from. Okay, so this is going to be one of the conditions, but we have to prove in order to show that we can really impose these conditions here on the polarization tensor is that we can solve these equations for alpha 0 and all the, and alpha I as functions of ki, k0, and epsilon 0 I, and also the trace of the polarization tensor. Now, if you do exactly the same calculation for the trace, okay, so now you are going to perform a transformation on h prime, okay, because h prime depends on is equal to epsilon prime rho sine kx, and now this is going to be the original h sine kx plus 2 times partial mu epsilon mu, and this partial mu, epsilon mu, is going to be with this epsilon here is going to be minus k mu alpha mu, okay, and sine kx, which now we can take as a common factor. And the second condition tells you that alpha mu k mu has to be with a factor of 2, sorry that I am missing, has to be epsilon rho rho. Okay, and let's expand this if we want to. So it's alpha 0 k0 minus alpha I ki equal to epsilon rho rho. So there is this condition and this condition, and now what we have to show is that you can solve for alpha 0 and alpha I in terms of k and the trace. There are different ways of solving this equation or showing that it can be solved, and in all cases what you do is that you use the condition that k is an odd vector, so k0 squared minus ki is 0, okay, so which is the same that you can replace this product ki by k0 squared always. Okay, you could for instance multiply this equation by ki and then use this condition, so you get here k0 squared plus ki alpha I k0, and this is equal to epsilon 0 I ki. And with this dividing by k0, you get that, sorry, this I should be down, is equal to epsilon 0 I ki divided by k0 minus alpha 0 k0. Now you can use this in this equation, and you find that times alpha 0 k0 is equal to epsilon rho minus epsilon 0 I ki divided by k0, and then you get divide again by k0, and you have by 2. Okay, and now you know what alpha 0 is and then what alpha I is. Okay, the particular values of alpha 0 and alpha I are irrelevant. We are not so interested in them. We just have to prove that they exist, that these conditions which translate into these equations can be solved, okay, and that you can impose in the end these conditions on the polarization vector tensor. Okay, so let me summarize the conditions that we have imposed. On one hand, we have shown that the Donder gauge implies these 4 conditions, and we also have imposed this condition on the trace, so the polarization tensor is traceless, and we have also imposed that these components are 0. These are 4 conditions, this is 1 condition, and these are 3 conditions in the 8 conditions, which leaves us with only 2 independent components. Okay, now the choice of independent components of the polarization tensor depends a bit on how you on the motion of the wave. Okay, we are going to make this standard choice, which is that k mu, the components of this vector, are just omega 1 0 0 1. This corresponds to a wave moving in the positive, in the direction of the positive x3 axis. With this choice of k, this first condition becomes epsilon well, I think here is mu, the one which is contracted, so it is epsilon 0 nu plus epsilon 3 nu is equal to 0. Okay, and this condition now becomes explicitly, this is epsilon 0 0 minus epsilon I equal to 0, and then we have the three conditions epsilon 0 I equal to 0. Now these are four conditions, so these are epsilon 0 0 plus epsilon 3 0 equal to 0, epsilon 0 1, and so on. Okay, so we put the I plus epsilon 3I equal to 0. Because of this, okay, now we have also that this is 0. Also, because these mixed components are 0, this one is 0, and this means that epsilon 0 0 is 0. Now we come here, and this is epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3 equal to 0. But, well, in particular, epsilon 3 3 is 0, so you arrive to this condition. And okay, the only component which is not related, that doesn't have a 3 here or a 0, because we have already exhausted all the conditions that involve them, is epsilon 1 2. Epsilon 1 2 is unconstrained. Okay, so there are three non-vanishing components at most. Okay, which are, at least these are the ones that are allowed by all these conditions. There are three that can be non-vanishing also under this assumption, and they are epsilon 1 1, epsilon 2 2, and epsilon 1 2. But epsilon 1 1 and epsilon 2 2 are not independent, they are related by this condition. So only one of them is independent and represents one degree of freedom, and the other degree of freedom is represented by epsilon 1 2. Okay, epsilon 1 2 usually is represented by epsilon x, by the reasons that will become evident in a little while. Epsilon 1 1 is called epsilon plus. Okay. And okay, with all these conditions, the result is that the polarization tensor for this particular K, okay, satisfying these conditions, is well, we can represent it in this way. Only this 2 by 2 box in the center is different from 0. Epsilon 1 1 we called epsilon plus, but epsilon 2 2 is minus epsilon 1 1, so it is minus epsilon plus. And this is epsilon x, because it is epsilon 1 2, and epsilon 2 1 is epsilon x as well, because it is symmetric. And the rest of the components are 0. Epsilon plus and epsilon x describe the two polarization modes, okay, in a certain basis. They can be used as a basis for the two possible polarizations of the gravitational wave. Okay, so now we know essentially what the solutions to the wave equation are in this case. Okay, the simplest ones are of this form. For a wave propagating in the positive direction of the x3 axis, okay, so it's epsilon mu times a sine, and then of course you could make wave packets by summing over many of these elementary waves. The meaning of the x and the plus in this that denotes these two polarization modes will also become evident when we discuss how do we detect these waves. They will be detected by their effect on free-falling particles. They will be affected by gravitational waves, and then you will tell me that, okay, but I cannot, if it is a free-falling particle, then I just don't see the gravitational field. If it is only one, that's true, but if you consider many free-falling particles, a set of free-falling particles, many free-falling particles that you can imagine that they fill a region of space, and when they move a region of space-time, they generate a congruence of geodesics. And as we have studied, when there is a non-trivial curvature, and this is a non-trivial metric, the metric associated to these gravitational waves, even if it is weak field and so on, it generates a non-trivial curvature, then these geodesics will be deviated by the curvature. And that is the way we will detect gravitational waves, as we will see. This deviation, okay, has to do with this X and this plus in the polarization, and this distinguishes, these different deviations distinguish the two polarization states, and this is something that we will see later.